Melting points and boiling points of group 14 elements are much higher than those of corresponding elements of group 13. The common oxidation state exhibited by group 14 elements are +4 and +2. All group 14 elements, when heated in oxygen, form two types of oxides, that is monoxide and dioxide. Interaction of between lone pair of chloride and silicon 4+ is not very strong. Hello everyone, this is Harshita Bhavasar from Vidhyaashram School of Excellence. Today I am going to start with session 4 from the chapter Some P-block Elements. In the last session we have discussed about diborane, uses of aluminium and its compounds, carbon family elements, its normal properties, atomic properties we have discussed from the group 14 in periodic table. In today's session, we will discuss about some of the physical and chemical properties of group 14, that is carbon family, and also anomalous properties of carbon and its allotropic forms of carbon. These are the contents which we will discuss in today's session. First, physical properties of carbon family. All group 14 members completely solids. Carbon and silicon are non-metals. Germanium is metalloid. In carbon family, carbon and silicon are non-metals. Germanium is metalloid, which is having the both characteristics of metal and non-metals. Tin and lead are soft metals with low melting points. Usually metals are hard and it is having solid structure, but tin and lead, with some exceptions, soft metals with low melting point. Melting points and boiling points of group 14 elements are much higher than those of corresponding elements of group 13. Comparative to group 13, group 14, that is carbon family elements, having higher melting point and boiling point in the comparative way. Next, chemical properties. In that, oxidation states and trends in chemical reactivity we will see. The common oxidation state exhibited by group 14 elements are +4 and +2. Carbon also exhibits negative oxidation states. Usually group 14 will exhibit +4 and +2. Carbon will also exhibit negative oxidation state also. Since the sum of the first 4 ionization enthalpy is very high, compounds in +4 oxidation state are generally covalent in nature. The first 4 ionization enthalpy, the sum of first 4 ionization enthalpy are very high. Usual oxidation number is +4 and they are generally in covalent in nature. Okay. In heavier members, the tendency to show +2 oxidation state increases in the sequence of germanium, tin and lead due to the inability of NS2 electrons of valence shell to participate in bonding, that is inert pair effect. In heavier elements, the tendency to show +2 oxidation state means in the heavier elements +2 oxidation state will increases in the sequence germanium, tin and lead. Why it is? Means it is the inability of getting NS2 electrons in the valence shell to the participation of bonding. So that effect will be considered as inert pair effect. The relative stabilities of +4 and +2 oxidation states vary down the group. Carbon and silicon mostly show +4 oxidation states. Germanium forms stable compounds in +4 state, only few compounds in +2 states. Usually we have told that usual oxidation state is +4, like carbon, silicon, germanium will follow. Other than that will show +2 oxidation state. Tin forms compounds in both oxidation state +2 and +4, but whenever it is +2 it will act as a reducing agent, and lead compounds in +2 state are also stable, in +4 the strong oxidizing agent. In tetravalent state, the number of electrons around the central atom in a molecule is 8. In tetravalent state means 4 valence electrons will be present in the valence shell around the central atom in a molecule, which will be 8. Being electron precise molecules, they are normally not expected to act as electron acceptor or electron donor species. Since it is having accurately 8 electrons surrounding the central atom, it cannot act correctly as expected electron acceptor or electron donor species. Although carbon cannot exceed its covalence more than 4, other elements of the group can do so. It is because of the presence of d orbital in them. We know that carbon cannot exceed 4 electrons in its valence shell. Although the elements are present in its group only, it will exceed. Why means it keep on getting the heavier atomic numbers, and there is an influence of d orbitals also. So, more than 4 electrons can be expected in other elements in group 14 but not in carbon. Next, due to this, their halides undergo hydrolysis and have tendency to form complexes by accepting electron pair from donor species. Due to that electrons accepting character is there in group 14 elements other than carbon. So, what will happen? It will react with halides and it will undergo hydrolysis by accepting electron pairs. For example, the species like silicon fluoride, germanium chloride, tin hydroxide exist where the hybridization of the central atom is sp3d2. Next, reactivity towards oxygen. All group 14 elements when heated in oxygen form two types of oxides, that is monoxide and dioxide. When group 14 elements react with oxygen, it will form two types of oxides, that is monoxide means one oxide, dioxide means two oxygen elements will be present. Silicon oxide only exists at high temperature. Oxides in higher oxidation states of elements are generally more acidic than those in lower oxidation state. In silicon oxide only exists as at higher temperature. Another point, oxides in higher oxidation state like +4, it will having more acidic in nature. Whenever it is having lower oxidation state, it is having less acidic or more basic in nature. The dioxides such as CO2, that is carbon dioxide, silicon dioxide, germanium dioxide are acidic, whereas tin dioxide and lead dioxide are amphoteric in nature. Among monoxides, carbon monoxide is neutral, germanium monoxide is distinctly acidic, whereas tin oxide and lead oxide are amphoteric. Here you have to observe tin oxide and tin dioxide, lead oxide and lead dioxides are completely amphoteric in nature, which is having the both characteristics of acid and basic nature. But carbon dioxide, silicon dioxide and germanium dioxide are acidic in nature, as well as its monoxides also acidic in nature. Reactivity towards water. Carbon, silicon and germanium are not affected by water. Tin decomposes steam to form dioxide and dihydrogen gas. Usually carbon, silicon and germanium do not react with water, but tin reacts with water by decomposing and formation of hydrogen gas. Lead is unaffected by water due to the formation of protective oxide film on its surface. Due to the formation of thin surface or thin layer on its own, so it will be completely unaffected by water. Here the only exception is towards tin. Next, reactivity towards halogen. Group 14 elements except carbon reacts directly with halogens to form furan halides of the type MX2 and MX4, where X can be fluorine, chlorine, bromine and iodine. Except carbon, others will react with halogen to form halides. Most of the MX4 are covalent in nature. The central metal atom in these halides undergoes sp3 hybridization and molecule in the tetrahedral shape. Tin fluoride and lead fluoride are ionic in nature. Usually, see, we have told MX2 type and MX4 type halides will form. In that, MX4 will always covalent in nature and it will undergo sp3 hybridization, but SN4, that is tin fluoride and lead fluoride, will be in ionic in nature. Lead iodide does not exist because lead and iodine bond initially formed during the reaction does not release enough energy to unpair 6s2 electrons and excite one of the more to them higher orbital to have 4 unpaired electrons around lead atom. Usually lead iodide does not form because bond initially does not form between that. It need to release enormous amount of energy. Next, germanium and lead are able to form dihalides of the formula MX2 stability of the dihalides increases down the group. As we go down the group in the periodic table, stability of the dihalides will increases. Thermal and chemical stability of germanium tetrahalide is more stable than germanium dihalide but lead dihalide is more stable than lead tetrahalide. Tetrahalides except CCl4 are easily hydrolyzed by water because the central atom can accommodate the lone pair of electrons from oxygen atom of water molecule in d orbital. Why this will happen means tetrahalides except carbon tetrachloride are easily get hydrolyzed by water. Okay, and the central atom can accommodate lone pair of electrons from oxygen due to the influence of d orbital. For that reason, the stability will also changes. For example, silicon chloride undergoes hydrolysis by initially accepting lone pair of electrons. See, the lone pair of electrons will be accepted by silicon. The hydrolysis is going to taking place from water molecule in d orbital of silicon, finally leading to the formation of silicon hydroxide. Here HCl will be removed and with hydrolyzing means with water will be treated, 3 HCl will be molecules will be removed and silicon tetrahydroxide or silicic acid will be formed. How that d orbital will be involved? There is one illustration. Silicon hexafluoride is known whereas silicon hexachloride not. Give possible reasons. This is due to the 6 large chlorine ions cannot be accommodated around silicon 4 plus due to the limitation of its size. Due to the small size in silicon 4 plus oxidation state, it cannot be seen. Interaction of between lone pair of chloride and silicon 4 plus is not very strong. Due to these reasons, silicon hexafluoride is known but silicon hexachloride is not known and it cannot be formed due to the small size of silicon and also it cannot form very strong bond in between them. Next, anomalous behavior of carbon. Carbon, the first member of group 14, shows anomalous behavior from rest of the members due to extremely small size, high electronegativity, higher ionization enthalpy and non-availability of d electrons. These are the usual reasons of very first members in all the groups to show the difference between other elements in the same group. So, extremely small size will be there. As we go down the group, size will increase, their electronegativity will decrease, but the first element will be having more electronegativity, higher ionization enthalpy. In the first element, there will be no d electrons will be involved. So, due to these reasons, carbon will show some of the anomalous property. The main points of difference with respect to the other elements of the same group are: in carbon, only S and p orbitals are available for bonding and therefore it can accommodate only 4 pair of electrons around it. Here only S and p orbitals can be seen and d orbitals cannot be seen. This would be limit the maximum covalency of 4, whereas other elements can expand their covalency due to the presence of d orbital. In the same group, other elements will expand its covalency due to the interference of d orbital, but carbon could not. Carbon forms p-pi multiple bonds with itself and with other atoms of small size and high electronegativity, whereas heavier elements do not form p-pi bonds because their atomic orbitals are too large and diffuse to have effective overlapping. Although carbon is having small size, but it will form p-pi multiple bond to form large molecules, but heavier elements with having more covalency, it will not form more bonding or p-pi multiple bonding with other and it will not extend its effective overlapping. Carbon atoms have the tendency to link with one another through covalent bonds to form chains and rings. This property is called catenation. Carbon also it is having the property called catenation. So, it will form covalent bonds to form chain, ring, branches, anything. That property will be called as catenation. This is because of carbon-carbon bonds are very strong. Catenation property decreases down the group due to their increased size. Due to carbon is having very small size, this catenation property can be exhibited very nicely. But as we go down the group in the periodic table, this catenation property will decrease due to its increased size. The order of catenation is carbon first, next silicon, germanium and tin. Lead does not show any catenation property. Due to property of catenation and p-pi bond formation, carbon is able to show allotropic forms. Due to this catenation and p-pi bond formation, carbon is able to show allotropic forms. The existence, see here, allotropic forms, why it will form? Because of the catenation property, because of p-pi multiple bond with effective overlapping. By these two properties, carbon will exhibit the allotropic forms like diamond, fullerenes, graphite. So what are those? How it will be exhibited? We will see now. The existence of an element in more than one physical state is called allotropy. The chemical substances could be little bit same, but physical property or physical state is completely different. That characteristics will be considered as allotropy. Here carbon will exhibit that property. The various forms are called allotropes. Carbon exists in nature in two allotropic forms, diamond and graphite. In 1985, third form of carbon known as fullerenes was discovered by H.W. Kroto, E. Smalley and R.F. Curl. For this discovery, they awarded the Nobel Prize in 1996. Okay. First, they discovered the two allotropic forms of carbon, that is diamond and graphite. Later in 1996, they showed fullerenes also a part, or a fullerenes is also a allotropic form of carbon. For that they are rewarded by Nobel Prize also. First we will see the properties of diamond. Each carbon in a diamond crystal is bonded to 4 other carbon atoms, making a giant macromolecular array or lattice. As each carbon has 4 single bonds, it is sp3 hybridized and has tetrahedral bond angles of 109 degree 28 minutes. In diamond, it is a crystal-like structure, but one carbon is attached with 4 other carbon because carbon is tetravalent. We know that carbon and carbon bonds are very strong, all are single bonded, so it is sp3 hybridized and it is tetrahedral in structure. Diamond crystal or grain of sand is just one giant molecule. Such molecules are rigid and strong, have very high melting point. We know diamond is a very strongest particle and it is having highest melting point. Each carbon atom forms 4 covalent bonds in a very rigid giant covalent structure, which makes diamond hardest natural substance. We know that diamond is the very hardest substance. This makes diamonds ideal as cutting tool. Diamond can be cut by diamond, we know that. Why this will happen? Because carbon is attached with another 4 carbon, which makes the bond strongest. All those strong covalent bonds give diamond a very high melting point. It does not conduct electricity because it has no free electrons. It is having high melting point and it does not conduct electricity because there is no free electrons in it. This is the overall structure of diamond, how precisely and how tightly it has been bonded. Next, graphite. Graphite is one of the allotropes of carbon and it has a macromolecular structure. Each carbon atom is covalently bonded to 3 other surrounding carbon atoms and graphite has a layered structure. In graphite, each carbon atom undergoes sp2 hybridization. Diamond sp3, graphite sp2 hybridization, and it is having a layered structure. The bond angle between the carbon atoms is 120. This structure is made up of flat hexagons. Okay, that is why it is showing layer by layer structure. These hexagons are joined together to form 2-dimensional flat layers. Therefore, each layer is giant molecule. So, the bond inside the hexagons within each layer is strong, but the bonds between the layers are weak. This weak bond between layers is called van der Waals forces. Each layer, whichever the forming a giant molecule, that bond will be strong, but inside the hexagon it will be weak. That weak layers will be considered as van der Waals forces within the hexagon, I am telling. This is the overall graphite structure. This one layer, this one layer, this one layer. In between it will be having low forces of attraction. That will be called it as van der Waals forces. Next properties. Since the bond of each layer of the graphite is strong, more heat is required to overcome intermolecular forces. Such graphite is having very high melting point. Between layer to layer it is having strongest connectivity. So, to break it we need high melting point. So, it is having very high melting point of 3675 degrees Celsius and boiling point 4200 degrees Celsius. The weak bond between layers makes the layers can slide over each other. Therefore, graphite is soft and slippery. Between two layers what will happen? Little bit weak forces are present and it can slide layer to layer, which makes graphite soft and slippery. So, it is used as a lubricant. The layers are held together so loosely that they can able to rub off onto paper to leave a black mark. That is how pencils work. The nib or the lead of the pencil will be holding off this graphite only. It can slide on a paper very easily. In graphite, each carbon atom has one outer shell electron that is not used to form covalent bonds. These electrons are delocalized. One electron is freely available in graphite. So, those electrons will not undergo the covalent bond formation. So, it can delocalized very easily. These electrons can move along the layers from carbon atom to the next, hence graphite conducts electricity. It can move from one carbon to another carbon, so it will conduct electricity very easily. Graphite is insoluble in water and organic solvents. It is because the attractions between solvent molecules and carbon atoms will never be strong enough to overcome strong covalent bonds in graphite. It is black, metallic and opaque. Next uses. Graphite can be best used in and as refractory materials, lubricants, brake linings, steel makings, expanded graphite, electrodes and pencil lead. These are the uses of graphites. Next is fullerenes, which is a third allotropic form of carbon. These are small molecules of carbon in which giant structure is closed over into spheres of atoms or tubes. Fullerenes were first isolated from the soot of chimneys and extracted from solvents as red crystals. This is small molecules, not a giant molecule. From the small molecules of carbon in which the giant structure will be formed as a spheres of atoms. But it was first extracted by the soot of chimney as a red crystals. The sooty material formed by condensation of vaporization CN small molecules consisting of C60, C70 and the traces of other fullerenes containing even number of carbon atoms up to 350 and above. The bonding has delocalized pi molecular orbitals extending throughout the structure and the carbon atoms are a mixture of sp2 and sp3 hybridized system. Fullerenes are insoluble in water but soluble in methyl benzene. Other forms of allotropic forms of carbon are completely insoluble in water and organic solvents, but this fullerene is insoluble in water but strongly in methyl benzene. They are non-conductors as the individual molecules are only held to other by weak van der Waals forces. It is completely formed by weak van der Waals forces of attraction or forces, and these are all non-conductors of electricity. This is fullerene structure. How? The tiny particles will form a ball-like or spear-like structure. Structure of C60 fullerene, what we have seen now. The smallest fullerene has 60 carbon atoms arranged in pentagons and hexagons like a football. Overall, 60 carbon atoms are present. In between hexagon structure is there, in between pentagon structure is there, and overall this hexagon and pentagon structure will combine to form a spear-like structure like a football. This is called Buckminster fullerene. This name comes from the inventor called Richard Buckminster Fuller after the discovery of C60 fullerene. This is who's scientist? Inventor of fullerene, C60 fullerene. To give his tribute, that name only showed Buckminster fullerene. C60 fullerene consists of 26 membered rings and 12 5-membered rings. Overall, 20 hexagons are there, 12 pentagons are there. All the carbon atoms are equal and they undergo sp2 hybridization. Each carbon atom forms 3 sigma bonds with other 3 carbon atoms. The remaining electron is delocalized in molecular orbital. This gives the aromatic character to molecule. Due to its ring structure in there, the delocalized electrons will give the aromatic nature of fullerene. C60 also contains double bonds. Carbon-carbon single bonded length 143.5 picometer. Carbon-carbon double bonded length 138.3 picometer. We know that double bond is always shorter than single bond. Okay, this is about the overall allotropic forms of carbon and the physical and chemical properties of carbon family. In the next session, we will discuss about oxides of carbon and silica. I hope you have understood completely whatever I have taught today. We will meet in the next session. Thank you.